Myelin causes that neuron to be able to fire faster. Why? Because it's got that fatty lipid layer with plasma membrane all wrapped around the axon, right? So it prevents the loss of charge. That decrement in current or that resistance, that loss of charge and that leaking out of charge, it actually allows that charge to stay in the axon and sort of jump from one region to the next. So instead of coming in and then losing some of that charge, the positive charge comes in and has nowhere to go. So it jumps or rushes from one node to the next, right? So it actually insulates it and allows the spread of charge to be much faster. Prevents that loss of charge or that leakage of charge. So charge comes in, sodium rushes, goes to the next one, pops those open, those come in. So just having this myelin lipid surrounding or layer speeds up the action potentials. Okay, so it insulates them. It allows the speeding of their cable-like properties, so they can really allow those ion currents to move fast. Now, of course, there has to be nodes because the nodes, that's where the channels are, right? So it can't be just completely covered in the myelin material. It has to have exposed areas where the ion channels are actually located. So the nodes of Ranvier allow the sodium potassium across the membrane. They're spread out every like 1 to 2 microns, so all the way along the axon. Sodium channels are concentrated at the nodes, and so are the potassium ion channels. These are the voltage-gated potassium and sodium channels that allow in and out that positive charge. So this causes APs to literally leap from node to node. So they go from one node to the next, like super fast, okay, because there's nowhere to go. Comes in and it moves, comes in and it moves. So instead of that loss or that decrement in those cable-like properties that an unmyelinated neuron would have, a myelinated neuron, on the other hand, that has heavy myelination, is going to have fast leaping of action potentials from one node to the next. That leaping is called saltatory conduction because it's almost like it leaps. Saltatory means to jump, right? Like kangaroos and stuff, they jump. It will jump from one node to the next. So that speeds that action potential up. So it increases the conduction velocity of action potentials. So neurons that are heavily myelinated and or big in diameter have much faster action potential speeds. That means they can go down from top of the axon to bottom of the axon, okay? So they fire faster, they're more quick, okay. So if we look at this, each one of these is the myelin sheath that's like a Schwann cell wrapping around a segment of axon with the nodes of Ranvier interspersed. And so for each of these, you have the spread of sort of current or charge. Sodium comes in and it can actually spread from node to node. Now notice, it can spread in either direction, but the typical direction is sort of anterograde firing, where it goes from top or axon hillock all the way down to axon terminals. And it kind of keeps going in that direction, making those saltatory jumps. This is supposed to show resting potential here in yellow, and then depolarization is blue, repolarization is red. So it'll go from one place to the next, all the way down, or going in that direction. Nope, just doesn't work. I wonder if I do that, I'm going to change the settings. Okay, all right. So I will have to, on the next lecture capture, I will try to play those videos and show those movies. And you can actually open up and watch them yourself as well. But they're nice because you can just step through and see what happens to the action potentials and how fast they actually conduct. So AP conduction speed is increased by those two main things I mentioned, right? Larger diameter of neurons, so the axon's bigger, reduces that resistance to spread of charges through those cable properties. So it reduces that resistance or that leakage of charge, so it goes faster. Myelination because of that saltatory conduction. So it's like insulation, it's like casing on there, right? And letting that flow of charge move from one gap to the next real fast. Examples are thin, unmyelinated neurons. How fast do they fire in action potential? From top to bottom, about 1 meter per second. So that means from like your spinal cord or the base of your spinal, the tail end of your spinal cord, all the way down to like your foot. That would be like 1 meter per second. Right? So that's about 1 meter distance, doing that action potential in a second. Very big neurons, though, that are thick, so they have a wider, bigger diameter, and they're myelinated, they can go 100 times that speed. So 100 meters, what's that? That's more like a football field, sort of, right? the length of a football field in 1 second. Very, very fast. And we'll see in certain organ systems in the body, you don't have to have super fast action potential speed for depending on what it is.